So in this video we are going to learn about Wilkinson catalyst. Okay, so the structure of this catalyst is rhodium metal is present, and then one chlorine is present, and then 3 triphenyl phosphine is present. So this is the main structure. Okay, so this is a coordination compound. So this is mainly an organometallic complex. They call it as an organometallic complex. So usually in organic metallic complex, the metal is directly attached to a carbon, but in this case there is no metal that is directly attached to a carbon, but still it is an organometallic catalyst or compound because it is basically undergoing hydrogenation of alkene. Okay, so this helps in hydrogenation of alkene. So during this process in the mechanism, there is a step where the metal, this rhodium metal, is directly attached to the carbon. Because of that step, it is called as a organometallic complex. Okay, so let's find out the oxidation state of this particular complex. Okay, so instead of this rhodium, I can just take it as X, and then for chlorine I am going to put -1. So why am I adding -1 means, see, we know that chlorine has totally 7 electrons. Okay, so if it is gaining another 1 electron, it will become 8. So 8 is an octet, it is completely stable. So in order to attain stability, it needs 1 electron. That's why we have written what? -1. And then for this triphenyl phosphine, we will just take it as 0 because it is already stable. So it is a neutral compound. Okay, triphenyl phosphine is a neutral compound. It has one lone pair. That lone pair will attach to the rhodium complex. It doesn't need any electron for stability, so it is 0. Okay, so the oxidation state will be X is equal to +1. Okay, so initially rhodium electronic configuration is what? 4d8, like outermost I am telling. Okay, 4d8 5s1. Okay, so in this case we take it as rhodium plus because we have found that it has +1 oxidation state. Then the electron will be lost from the outermost shell, that is the 5th shell. So the total number of electrons will be 4d8. So this is the configuration for this particular complex. Then let's move on to the structure of this particular catalyst. So before finding the structure, first we have to know the hybridization. Then only we can find the structure, right? So first to find the hybridization, we are just going to write this. Okay, 4d8. How can we write 1, 2, 3, 4, 5? So this is 4d shell. There are 5 shells. 1, 2, 3, 4, 5, 6, 7, 8. Okay, then 5s is empty because this electron is lost, and then 5p is present. Okay, then what is happening is this triphenyl phosphine is a strong ligand. So whenever a strong ligand is this chlorine is a weak ligand, but then this triphenyl phosphine is a very strong ligand. So this strong ligand will cause pairing of electrons. So what will happen in the next step? 1, 2, 3, 4, 5. So there will be pairing. Okay, so then one D shell will be empty. One D shell is now empty. So how many ligands are present in this Wilkinson catalyst? Totally 4 ligands are present, right? 3 triphenyl phosphine and 1 chlorine. So each ligand will need a particular subshell. So this is D, this is S, and this is one P and another P. So 4. Okay, so the hybridization will be DsP2. Okay, so this is nothing but square planar hybridization. So the geometry will be what? Square planar structure. Okay, so square planar structure means one metal is present and then 4 ligands are present in the sides. So only 2 axes will be present. Okay, x-axis and y-axis. So you can consider a square planar as a table. Okay, in the table, in the center, metal is present, and surrounding that center everything else, whatever ligand is present, that is surrounding that place. Okay, so this is a square planar structure. So now we can find whether it is chiral or achiral, or whether it is having geometrical isomerism from this. Okay, so in order to find that, so whenever a particular compound is chiral, it will not have any plane of symmetry or center of symmetry, anything. But this compound will have a plane of symmetry. Consider we are passing this particular plane. So all the atoms will be covered and all the things are cut equally. So basically it has plane of symmetry, that is this horizontal plane of symmetry is present in this compound. So since plane of symmetry is present, it is achiral. Okay, so achiral means nothing but optically what? Optically it is inactive. Okay, then what about the geometrical isomerism, whether it is having means? So in order to find the geometrical isomerism, what we have to do is we have to consider the ligands. Okay, consider chlorine as ligand A. Okay, then triphenyl phosphine as ligand B. Only two ligands are present. So one chlorine is present and three triphenyl phosphine is present basically, right? So we have to take these in pairs. So how many different types of pairs we can form? That is the number of geometrical isomerism. Okay, so AB and BB. So this is the only type of pair we can form. So that is not having geometrical isomerism. Consider another example for in case to understand A, B, B. Consider if this is the ligands, then what we can consider A, B, B. And another thing we can write AB, AB. So these are all the possibilities. So then it is having two geometrical isomerism. But if it is only one way we can write it, means it is basically mean no geometrical isomerism. So for the in this case, rhodium catalyst, that is this Wilkinson catalyst, is not having geometrical isomerism is also not there, and optical isomerism is also not there. So stereoisomerism will also be not there. Okay, because stereoisomerism contributes to these two factors, so nothing is present in this case. Okay, then what about the addition? How the addition is taking place? Consider this is the alkene. So hydrogenation will be happening in this position. Okay, this 1 and 2 position. Okay, so the product will be hydrogen, either this or it can be. So basically the hydrogen is added in same side. Syn addition will be happening. So these will be the products. The products will not be like this. Okay, one hydrogen is the below and then other hydrogen is above. So this is not the product. Okay, so these two products are the possible ways. Okay, then move on to the IUPAC name. So IUPAC name. So it is very important. So in case of this rhodium catalyst, one chlorine is present, right? So and then 3 triphenyl phosphine is present. Okay, so C is present. Chlorine is start from C, and then for phosphine, triphenyl phosphine is phenyl is starting from P. Okay, C is the first one in alphabetically. So first we will write the ligands in alphabetical order. So chloro, and then triphenyl phosphine or 3 is present. See, triphenyl phosphine is present 3 times. So we cannot write triphenyl phosphine. Instead we have to write tris and then triphenyl phosphine. Okay, so this is the correct way to write triphenyl phosphine, and then rhodium. We will write rhodium. That is the metal. So first we have written the ligand and then the metal, and then we will finish it with the oxidation state. We already found the oxidation state is what? +1 oxidation state. Okay. Then it can be called as a homogeneous catalyst. Okay. Homogeneous catalyst. So what is mean by homogeneous catalyst means? So basically it is soluble in the reaction mixture. Soluble in reaction. So whatever reaction we are taking place in, this catalyst is soluble in that reaction mixture and then gives high product selectivity. So whatever product, so consider 2 products are formed, so it is giving high product. So one particular product will specifically in higher percentage than another product. Okay, then the one disadvantage is difficult to separate from whatever, see, consider product will be formed and the catalyst will still be there. So it is quite difficult to separate the catalyst and the product. So that is the only disadvantage. Okay, so in the case of heterogeneous catalyst, what will happen? It is insoluble in reaction mixture, and then it is very less, it is giving less product selectivity, less selectivity is there. But the only advantage is Easy to separate. Easily we can, just by filtration we can separate the product from the catalyst. Okay, easy to separate. So what is an example we can take is nickel hydrogen catalyst, the most common one. Okay, so most of the organometallic complexes, or what means homogeneous catalyst. Okay, so the general reaction, then we will see about the diamagnetic or paramagnetic nature. See, in this case, if you see, this is the rhodium plus in the paired form, right? Paired, after ligands are attacking, it is in paired form. So all the electrons are in paired state. No one is in separate form. Initially it was separate, after it got paired, right? So it is a diamagnetic compound. Okay, now whenever it is the electrons are paired, it is called what? Diamagnetic compound. Okay, so let's move on to the general reaction. So consider this is present, it will be converted into what? So here one H will be present. Each carbon will have totally 4 bonds. Just remember that. Okay, so what will be the final product? 3 hydrogen this side and then 2 hydrogen this side. So here one hydrogen is bound, here one hydrogen is. So each bond is taking 1 hydrogen. So we will move on to the mechanism. So this is very important mechanism part. So in the mechanism, the first step is oxidative addition. Okay, so what is mean by oxidation? Oxidation means loss of electron is there. So the oxidation state will be increased, and the coordination number will also be increased. That is called oxidative addition. Something is adding. Okay, so see, rhodium is present, and then we know that triphenyl phosphine 3 times, it is present 3 times. 1 chlorine is present. Okay, so what is the oxidation state here? X is equal to +1. And what about the coordination number? Coordination number is 4, because 4 ligands are directly attached to our metal. So coordination number is 4. So now we are adding hydrogen. So hydrogenation is going to happen. So hydrogen is added. Okay, so mostly in this oxidative addition, the neutral ligands will be added. So hydrogen is a neutral ligand. Okay, so now what is happening is, so this hydrogen is going and adding in the cis position. Okay, so these both are cis position. So when it is trans means they will be opposite to each other. Okay, so cis position it is adding. Okay, hydrogen, and then PPH3, 1 chlorine is present, and then PPH3. So this is the new compound. So this is having octahedral structure. 6 ligands are attached. So the coordination number will be what? 6, because 6 ligands are directly attached. And what about the oxidation state of this particular octahedral complex means? For rhodium we will take it as X, and then for each hydrogen we can put -1. Why? Because hydrogen actually has only 1 electron. If it is adding another 1 electron, what will happen? It will give 2 electrons. So 2 electron is more stable for hydrogen case, because in 1s2 orbital that maximum electron is only 2 electron. So that is having high stability. So they are gaining electrons. So that's why we are writing -1. And then for 1 chlorine I am putting -1. And then rest every neutral ligands will be 0. So X will be in +3 oxidation state. So from +1 it is converted into +3. From 4 it is converted into 6. Coordination number, this is coordination number, this is oxidation state. So basically 2 times everything is increased. So this is called what? Oxidative addition. So very easy step. Okay, then what is happening is dissociative mechanism. So what is mean by dissociation? So dissociation means something is released, something is dissociated or removed, something like that. Okay, so why we have to dissociate? So before moving on to that, we will see we have learned about 18 electron rule, right? So basically what is mean by 18 electron rule means, so if a particular complex is having 18 electron, then it is very stable. That is what is called 18 electron rule. Okay, so I forgot to explain that 18 electron rule. See, So there are two methods to find this. Either neutral method or oxidation method can be used to find this. So I am going to use oxidative method. Okay. So consider our rhodium complex. See, I am going to find 18 electron rule, whether it is following or not. Okay. So rhodium, what is the electronic configuration? 4d8 5s1. And for rhodium plus, because the oxidation state is +1, it will be 4d8. So for rhodium I am writing 8 electrons, and each ligand will contribute 2 electrons, most of them, but there are cases where it will contribute more than 2 or 1 electron. But in this case, see how we are able to find this metal is attached to a chlorine. So here 2 electrons are basically needed to attach to chlorine, so 2. Okay, and then similarly for metal is attached to triphenyl phosphine, there also 2 electrons is there to bond between metal and ligand, that's why 2. Okay, so 3 2s are 6 because 3 triphenyl phosphine is present, so basically 16 electron is present, so it is quite an unstable catalyst, rhodium catalyst. Okay, so now whatever product we got in this oxidative addition, we are going to find whether it is following 18 electron rule or not. I'll tell you why we have to find. So for rhodium, what will be the electron? So rhodium 4d8 5s1, that is the general form, but in this case the oxidation state of rhodium is 3 plus. So basically 3 electrons is lost. So what will happen? 9, initially 9 was present. Now 3 electrons are lost, so it will be 6 electrons. Okay. Then for each ligand we will take 2, right? For 2, for each hydrogen I am adding 2. And then for 1 chlorine it is 3, 1, 2. And then for 3 triphenyl phosphine it is 6. So totally 18 electron will be completely filled. Now, whenever this 18 electron is completely over, is highly stable. Okay, so it cannot gain more than that. Some incoming electron, whatever ligand, it cannot attach to this catalyst anymore because it is completely stable. Okay, 18. So now we need to add olefin. So basically the use of this catalyst is to reduce the alkene, right? So this compound needs some space where it can add the alkene group. So we are going to make that space, that is done by dissociative mechanism. So basically we are going to remove this triphenyl phosphine. Okay, so why not remove this chlorine? Why are we removing this means? Chlorine is quite small in size than triphenyl phosphine, so it is not giving that much space. So alkene is quite big, means it needs some space, right? So instead of chlorine, we are this is perfect to remove triphenyl phosphine for more space. Okay. Another thing you have to notice is that so the one group opposite to this hydrogen only will be removed. Okay. So hydrogen is present here, and another triphenyl phosphine is present here. Okay, so whatever triphenyl phosphine, whatever ligand is opposite to a hydrogen, it is more labile. Okay, labile means it is easily removable. So we are going to remove this triphenyl phosphine. So this is called dissociative mechanism. Okay, triphenyl phosphine is there, chlorine is here, triphenyl phosphine is there, and then here there is an empty space. Now there is space for our alkene. So now what will be the next step? Of course alkene is going to add in the next step. Okay, so this is the alkene group. So now our alkene group is going to this vacant space. Okay, rhodium, hydrogen, hydrogen, triphenyl phosphine, and then chlorine, and now our alkene is attached here. Okay, so now what is the next step means? So this is the slow step. So slow step means it is the rate determining step. So it is migratory insertion. So rate determining step, this is called migratory insertion. So basically in migratory insertion there will be 2 steps to follow. Okay, so the first step is what means one ligand from the compound. From the catalyst, one ligand is shifting its space and reaching to another ligand. So basically this hydrogen along with this 2 electron, it is taking that and coming to this particular position here. Okay, and then here 2 electrons will be present in this bond, right? That 2 electrons will go and attack to our metal and a bond is formed there. So this is the first step of migratory insertion. Okay, so rhodium is present, hydrogen is present. Now in this space there is empty space. From here only we are removing hydrogen, and then PPH3, PPH3, chlorine. And then what is happening? So consider this is the 1 position and this is 2 position. So this is 1 comma 2 migratory insertion, okay. So this is the main step. Okay, so in the 1 position, see, we are adding the hydrogen in the 1 position, and this carbon is attaching to rhodium. Okay, so carbon is attached. This is carbon number 2. So this carbon has 2 hydrogen, and here 1 hydrogen, and then OR group. So this is the first one. So this hydrogen is got from here. From here we are taking this hydrogen. Okay, next what is happening in this migratory insertion is, so this entire compound, see, this entire compound is this electron along with this 2 electron, it is going and attacking in this space. So from there only we took the hydrogen left, from there it is going there. This entire group is going to move to that space. Okay, so rhodium and then hydrogen is present. So here CH2, H2, C, H, H, R. Okay, and then here triphenyl phosphine, here 1 triphenyl phosphine, and then 1 chlorine. So here now empty space is present. So here this is the main step. Migratory insertion is very important. Okay, then what is happening is reductive elimination. Reductive elimination is happening. Reductive. So what is mean by reduction? Reduction means something is gaining electron. In this case metal will gain electron. So whenever something is gaining electron, the oxidation state will be decreased, right? And here elimination, so basically 2 ligands are eliminated from this entire thing. So it is called the coordination number will also be decreased. So it is like the opposite step of oxidative addition. Okay, so when this reductive elimination will happen means when both these ligands, so we have these ligands, right? These 2 will be removed. Okay, so when both these ligands are in cis position, then only this is going to happen. Okay, so what will happen is this electrons, there is 2 electron here, along with this 2 electron it will go and attack the hydrogen, and then what will happen here is this 2 electron is present here, that will reach our metal. So that is giving electron to our metal. Okay, so that's why metal is gaining 2 electron. Okay, rhodium, PPH3, chlorine, and then PPH. This is the final product. Along with this we are getting 1 alkane, CH, and this is also formed. Okay, so this is like the main step. So here this one is T shape. So this particular compound is T shape. So whether how to find if it is reduction means, so here what is the oxidation step? In this case it is for hydrogen we can put -1, and this alkyl group we can put -1, and this chlorine we can put -1, others 0. So X will be +3. So if you see here only chlorine is present, so X is +1. So from +1 to +3 to +1, it is of course reduction because 2 electrons are gaining 2 electron. And you see the coordination number. So initially the coordination number is 1, 2, 3, 4, 5. 5 is the coordination number. Here the coordination number will be what? Only 3. So here we saw that it is an organometallic catalyst because the metal is directly attached to our this carbon, right? So this is the step. See, this is the carbon and this carbon is directly attached to the metal. Okay, so this is representing what? Organometallic complex. Okay, next we can move on to reactivity order. Okay, reactivity order. So this is very important. Most competitive exam will have these questions. So consider an like isolated and a conjugated compound. Okay, sorry. CH2C or. So this is like a conjugated compound, and an isolated compound is present. Which will be more reactive means, of course, our isolated. Why means isolated compounds will have less steric hindrance, so easily this particular compound can fit into our catalyst, and then easily reaction can happen. But in this case it is quite big, this conjugated compound, so it is not easily fit, so the reaction will be little bit slow. Okay, then consider this particular part. This is the external, that is the terminal alkene. This is 1, consider this is 1 and this is as 2. Okay, so which will be more reactive? 1, because this particular space is like little bit less sterically hindered, right? So here it has a OR group, so it is quite difficult to reduce in this space. Okay, so terminal alkenes will be easily reduced than what the center one. Okay, then consider alkyne and alkene. Which will be reduced means alkyne will be more reactive. Then consider cis alkene and trans alkene. So in this case cis will be more reactive than trans. Okay, so basically we have to check for steric hindrance, that is the main point. So there is a reactivity order, so only one OR group is present here, and then this is a cyclohexene. So this is cyclohexene, and then 2 OR group or in the same side, and then 2 OR groups or in different sides cis position, and then 2 OR groups or in trans position, and then 3 OR groups are there, and then finally 4 OR groups are there. So this is the reactivity is will keep reducing because the number of OR groups are increasing. So this is a general reactivity order. So we have ignored alkene group. If you see, I have not written alkene group because alkene cannot be reduced to ethane by using Wilkinson catalyst. Why? Because we know that in the reaction, in the mechanism, we have to oxidatively add hydrogen, and then we have to dissociate PPH3, and everything will be present inside particular solution in the reaction. So what will happen is, instead of this hydrogen, this particular alkene is very reactive because it is very less sterically hindered, no OR group, nothing is present, so easily it will go and react with our catalyst. So this hydrogen will not have an opportunity with react with the catalyst. So once the hydrogen is not in the catalyst, the hydrogenation is not possible. So this is like a simple disadvantage of our particular catalyst. Okay, so thank you for watching this video. Like, share and subscribe.